Fluids in the news. Well, of course, there's the unfolding tragedy in the Philippines, I guess, from this typhoon. And so I guess I haven't really seen much of it because I haven't been looking at the news lately, but it looks all, the expected 10,000 people who've perished. I can't imagine that's going to be unfortunately, the end result on this. It seems very reminiscent of all the stuff that was going on in Japan in March of 2011 with this tsunami. Obviously, a very different event, but still fluids mechanics related. It's a little bit similar to tidal waves, I guess. And I was just thinking this morning that you have enough to be able to understand at least some of these, just in terms of what we're talking about in this class. We mentioned the other day that when you have we were dealing with Superstorm Sandy, I guess, this time last year, if this is the West Coast. So if this is New York City, then when you have a storm that's coming on shore, you get at least two effects. And I guess what made Sandy so terrible was that it coincided with already a high tide, and then the storm, in addition to that, added to that. And there are at least a couple of effects that are relevant to these kinds of things in determining how the magnitude of the tide, which really it is just a very high tide, which was the problem. And I guess the high tide is driven by a couple of things. It's driven by the pressure distribution in the storm. And so if you look at, for instance, a section across the storm in terms of the pressure distribution, and you kind of draw that. And I think it's the same exactly for this unfolding tragedy in the Philippines. And if you look at how the pressure changes as you go across the eye, then the pressure in the center of the storm is depressed over normal atmospheric, which might be something like 1,000 millibars, which is obviously 1 bar, which is 1 atmosphere. All these synonyms, which is, we know that 1 atmosphere is 100 kPa, so 0.1 MPa. And so the depressed pressure in the center of the storm might be something of the order of 900 millibars. And so if you look at this depressed pressure, it's depressed by 0.1 of a bar, 1/10 of a bar, and so that is 0.01 of a megapascal. So 0.1 bar is going to be equal to 100th of a megapascal, or roughly 10 kilopascals. And so if you think about the surface of the ocean, what that physically means to that is that this pressure here is lower than that. So if you imagine what the ocean must look like, then it bows up to be able to deal with that. And what we know about from fluid statics now is if you go horizontally in a static fluid, it's not quite static, but it probably is to some reasonable approximation, then the pressure at this point has to equal pressure at this point. And so if the pressure at this point is equal to 0.1 MPa, and this pressure here at the surface is equal to 0.1 MPa minus 1/10 of that, then this height here has to be, to catch up with it, the pressure change has to be equal to the difference in these. And so the difference in these, that in going up from here, you have to subtract off a pressure to be able to equal this amount here, and this change in pressure has to be 10 kPa. And so if you just do the rough math, the unit weight of water, gamma z, is equal to 1 meter times 10 kPa, roughly. It's 9.8, but it's basically 10 kPa, or 10 kilopascals per meter. And so this basically is 1 meter. So you'd expect the storm surge to be something of the order of add 1 meter to whatever the tides are. So that's one of the effects. The other effect that you have going on is that you have this rotation of the storm, and you have stronger winds onshore to the north of it than you do to the south of it. I'm not sure whether that switches if you're in the southern hemisphere. But anyway, on one side of the storm, if you have this rotation, you have a larger velocity on one. Well, you have the same velocity on one side, but it's onshore in one case and offshore in the other. And so I suppose you could also do the calculation where you look basically at this length of sea that has some velocity pattern above it. And I suppose, so this is just out of curiosity more than anything else. So if you look at the wind velocity versus elevation above the sea level, then I suppose it would look something like this, right? Close to the sea, because it's contacting the sea, it's going at zero because it's kind of attached to the water. And up here, it would be going at the atmospheric velocity, which might be, I don't know, 200 miles an hour. Or actually higher, right? Actually, the jet stream moves at something like that. And so there's this difference in velocity that occurs here. And so we know from Newton's law of viscosity, for instance, that viscosity times the change in velocity with location. So this is velocity in the x direction, but with vertical location here, drives a shear stress. And so if you think about it, that shear stress is being applied onto the top of the ocean. This length might be, I don't know what that length is, it's some length here. And so what you could do is you can do a simple calculation, just a free body diagram. I guess I can do it here. Is if you looked at what the effect of that would be, you have this tapering wedge. It's kind of pushing the water up with some force, and there has to be a force that's pushing back on this side. And this force would be some unit weight of water multiplied by some height. And so this force would be equal to what? Well, we know from fluid statics as well. Force is equal to the pressure at this point at the bottom multiplied by this height, half of that overall because it's half of this, and the resultant force is something like a half h squared gamma w. And so this is the force that's acting here. It has to counteract this other force that's acting here, and this force has to be equal to tau times whatever the fetch of this thing is. And so you can write an expression where you just balance this force here with this force here. So if you write F is equal to S, then you have a half gamma h squared is equal to the shear stress, which is viscosity, change in velocity with elevation, and the length of fetch, right? And so if you start putting numbers in this, you can figure out exactly what this storm surge would be. And so I guess you can just rearrange it, that h is equal to 2 over unit weight of water, viscosity, change in velocity over length, multiplied by length. This is vertical length. So what are some numbers for this? Unit weight of water is 10 kilonewtons per meter cubed. Viscosity for air, which is what is dragging on this, is something like 10 to the minus 5 Pascal seconds. The difference in velocities between being up here and being zero here, I think we did this for our speed of sound calculations. So 600 miles an hour speed of sound was something like 300 meters a second. So this should be about 100 meters a second. So 10 to the 2 meters a second. It all depends over how quickly you think this velocity changes from a big number where it's unimpeded by the surface of the ocean to zero at the ocean. So it could be a kilometer. I don't think it is. I think it might be the order of a meter or tens of meters anyway. So let's take one. And the length of fetch. And so certainly for the diameter of these storms, it's certainly 100 kilometers. Not sure whether it's 1,000 kilometers. Let's use 1,000 because I think the numbers are still very small. So 1,000 kilometers would be 10 to the 6, right? Meters. And this is all square root, right? So this is. And so what does that come out to be? That should be the height of the surge. In addition to that, anyone got an answer for me? Square root 2 is about 1.4, right? Take that out. So we have 10 on the bottom. So this is minus 6 times 6. So this is it 10 to the 2 divided by 1 square root 10 to the 2, which is 1 meter. Yeah. I think that might be right. Actually, that's a better number than I got when I was trying to do it in my head when I came into class today. And so you have the two effects. You have the fact that you drop pressure at this center, and therefore you get this storm surge because you have this welling up of the water just by the fact that you have a decreased pressure in the eye of the storm, which is of the order of a meter in this. And in addition to this, you get the influence that the water is being piled up against the side of the coast by the fact that you have this shear force by the wind being generated along it. And so you need to use this is 1,000 kilometers, right? 10 to the 6 meters. And that's of the order of a meter or so as well. So a couple of meters. They're talking about this wall being multiple meters tall. I guess the other effect that you have as well, if you think about it, and you see that with waves breaking on a beach as well, if you think about the shoreline looking like this, and the actual sea bottom is looking like this, then you can kind of think of waves as being a flow rate which is equal to a velocity times an area. And if this cross-sectional area reduces as you come on land, then it tries to speed up. It can't speed up because it's got inertia, and as a result it gains height just as breaking waves. And so we know that tsunamis, which are kind of tidal-ish waves offshore, are really a few centimeters tall, but when they come onshore, they're influenced by the fact that this shortening of reduction in depth occurs as you move onshore, and they pile up against the shoreline and move in with this big plug slowly, just raising the ambient level and moving inshore. So that's kind of so you certainly have enough fluid mechanics to be able to look at those things today. But that's not what we're talking about today, of course. But that's the reason for the unfortunate circumstance in the Philippines. What we were going to talk about today was our continuing quest to understand something about flow in pipes. So it builds on the things that we've talked about so far. And two things that we'll talk about are pipe networks and how to measure flow rates. We've talked a little bit about flow rate measurements with Venturi flumes in the absence of viscous effects, which now, of course, we're incorporating, bless you. And so let's see what we have on here to look at this. Well, flow in pipes, we didn't really talk about this at the time, but we mentioned it. The Deepwater Horizon problem was actually a failure in the material around it. I guess this is the picture of what is thought to have happened. This is a paper in the Proceedings of the National Academy of Sciences that looked at the behavior offshore. The idea is as you go down, you have these multiple nested casings. You start off with a big hole, you drill to some depth, then you put a smaller hole beyond that, and you case progressively narrower and narrower bore until you get to the reservoir. In this case, at 18,000 feet below sea level, which of course is 3 miles, just amazing. The sea level there is a mile deep at the location in the first place. And what is supposed to have happened is that you have overpressures here by the fact that you're compacting the sands. They really aren't reservoirs as you think of them, but they're very loose sands. As you put more material on top of them, they take the weight of that material that's put on that and they push that in the fluids column. The fluids column are the hydrocarbons and the waters that are in here, which are just the same idea as if you take a sponge and you put a sponge in a Ziploc bag and you loaded it, the sponge would actually take that load because the fluid can't get out. If you take the sponge full of the water and you just compress it, well, it'll just compress. But if you stop the fluid going out of it, then it actually becomes quite rigid and can take a much larger load. And reservoirs are kind of like that, soft reservoirs. They have very low permeability. The fluid can't escape, and so it's like being in a Ziploc bag. And so you can get overpressures. So if you look at the pressure column as you go down, you can end up with fluid pressures which are actually much bigger than the lithostat. In other words, the weight of rock that you have sitting above you. And when you get larger than the lithostat, it fractures it naturally and tries to get up. So what happens then if you have a very large pressure column in your well bore, as you did here, with these potential fluid pressures, they're underneath the overburden stress because that's what limits them. They'll frack it to be able to release pressure if you get high. But if you have a well bore which now all of a sudden links this large pressure at the bottom with the formation all the way up, then you end up with a very large pressure, potentially this pressure acting here, being able to break out of the casing and break out of the well casing. And I think that's exactly what happened, is that you had a large overpressure in the hole, you had some feature in the casing which wasn't quite right, it ruptured the casing, and all of a sudden it came out on the outside of this, and with the tragic circumstances that unfolded after that. So that's certainly piping in some respect. We're talking about pipe networks today, and of course pipe networks are used to transport all kinds of things around the country, gas being perhaps the most notable of them. And we'll look at very simple networks and nothing like the complex networks that take the fluids from the Gulf where they're produced, and now in Pennsylvania of course as well, into the areas where they're used, which is the population centers of the Northeast and the Ohio Valley. And so, and so you probably know, or perhaps you don't know, I think we perhaps alluded to it in this class. Well, no pictures in here? I thought it was in here. Gas storage. I guess I thought there were pictures in here. No pictures? Oh yeah, okay. And that if you go up to northern Pennsylvania, there are salt deposits. And in those salt deposits, there are caverns. Caverns are basically just long drill holes. You pump water into it to dissolve the salt. As you dissolve the salt, you get this long cigar-shaped cavity that you fill with water when you don't need it. And then when you want to store gas in it, you just put gas in it. The salt is very low permeability, so it's quite well sealed. And then you displace the water up onto the surface while you have gas in it. And then when you want to recover the gas, you just pump the water in and the gas comes out, and you ship the gas elsewhere. And I didn't realize this until a meeting in China maybe a couple of years ago, that in Belgium they actually use abandoned coal mines to put natural gas in, which seems interesting because they're not particularly well sealed, but they apparently do that. And of course the Strategic Petroleum Reserve in Louisiana and Texas is petroleum, crude oil, which is kept in salt caverns as well for times when, to kind of ameliorate shortages which are maybe promulgated on a political basis or for any other reason. A couple of years ago now, I guess 3 years ago, San Bruno is right next door to San Francisco Airport, where we saw the car being blown off by the jet engine. There was a gas pipeline that happened to go through a neighborhood, I guess as they're talking about in State College, which went up and killed, I guess, 8 people. And lit up the sky and just devastated the place. So there are some inherent risks with the fracturing of these pipelines. We talked before about tsunami warnings, the idea you could have ocean bottom seismometers offshore which get the signal of an earthquake very early, radiate it by EM waves, by an electrical signal, by sending a signal along a line. It arrives at the speed of sound, and so you get some tangible warning before the earthquake waves arrive. Well, you can do the same and this is installed in California, is you have cutoff valves in gas mains so that when there's some shaking, it shuts off the supply to your house. And so if the main ruptures in your house, it doesn't matter because there's very little initial gas in it. And so it's as a precaution to be able to do that. And of course, the other thing is that on a bigger sense, there are also sensors which will shut off large transmission lines for gas as well on the kind of industrial scale. And so, again, looking at behavior in this. We looked at this, big pipes. In this particular case, looked like an explosion at an underground turbine plant in Russia. We looked at the movies from it. I'm not sure if this is the movie for it or not. Yeah. And so what it was, I read it last night, was that there's a high reservoir impounded behind the dam. That's what the dam's for. You bring the water down to river level at the base of the dam, so you have this head loss, which we know how to calculate the energy that you'd get from that from our energy equation stuff. I guess I could do that. And in this particular case, it runs through, in all cases, it runs through turbines. It's under relatively high pressure. And in this particular case...
Almost a month since the Sayano-Shushenskaya power plant tragedy, new CCTV footage.
Yeah, so you see these unfortunate people happily doing whatever they're doing, and all of a sudden, what happened was that the water supply into one of these turbines, the turbine went off kilter and broke apart, and so now the water that's rushing through that turbine is uncapped and then unleashed into the whole of this turbine hole, which would be present in the base, basically in the rock in the base of the dam. And as a result, obviously, a large number of people unfortunately lost their lives. But again, fluid flow in pipes and the vagaries of having something go wrong in that particular case. That's a backup for septic systems. Don't really, kind of unsavory this time in the morning. Unsavory any time, perhaps, but especially this time in the morning. And I can't remember. Oh, it's okay. We'll deal with that later. So mutating disk engine. And so we'll talk about that if we get to talking about flow rate measurements. All right? So anyway, so that brings us back to talking about pipe networks. And so pipe networks are relatively straightforward, as you can imagine. So the idea is that instead of having a single pipe, you have multiple pipes in some kind of arrangement. And you could imagine the different arrangements that you would have. And they fall into two main categories. Those are either in series or in parallel. If they're in series, the requirements has to be that the amount of fluid flowing across this surface has to be the same amount flowing across this surface, and this surface, and this surface, these arbitrary surfaces that we cut it. And so we know that the volumetric flow rates have to be the same. And so what that physically means is that the head loss that we have on these, we know what the flow rates are. I guess we could write these flow rates also as the velocity 1 times A1, and also as the velocity 2 times A2. And we know that the head loss over these sections is a function of the velocities and the lengths and diameters of pipes. And so what we would assume is that the head loss as we go from this upstream location at point A to this downstream location at point B would just be the sum of the individual head losses that occur on each of these pipes. Makes sense, right? If we know what the volume flow rate therefore the actual velocity in each of these pipes are, then we can calculate the head loss should be equal to the friction factor, length over diameter, and velocity head term, where this velocity head is the velocity in the pipe, right, in the actual fitting. And so we'd have a loss in this pipe, we'd have a loss in this pipe, we'd have a loss in this pipe, and in the fourth one. And if you add those components together, it would give you the total loss over the whole transit through that pipe. So that's series pipes. And it's analogous actually to series flow in reservoirs as well. You could think of that, but we're not talking about that here. So parallel pipes, the behavior is something that the flow rates now are independent. So you could have a flow rate occurring in this one pipe and a different flow rate occurring in the second pipe. But what will control these flow rates relative to each other is the magnitude of the head drop that you have between these upstream and downstream reservoirs. So again, if this is a big reservoir assumption, we can assume the velocity at this surface point is 0. And because the head drop between this upstream location for pipe 1 is the same as the head drop as it goes through pipe 2, we know that instead of the flow rates being the same, what's the same in these cases is that the head losses in each of the individual pipes has to be the same in this case. So the things that are the same for series, the flow rate has to be the same in every single pipe. In parallel, the head loss has to be the same in every single pipe. And the corresponding magnitude is just the sum of the flow rates. Well, obviously, the flow rate in here plus the flow rate in here plus the flow rate in any other pipe you have would be the cumulative exchange of fluid between the upstream reservoir and the downstream reservoir. So that's really the rule that we have to remember for simple multiple pipe systems. Okay? And we'll do a couple of examples that illustrate this. What happens if we have pipe loop systems that are in some way defined? So in this case, we have a bifurcating pipe that's supplying fluid at some higher elevation here to some lower elevation here. And there's a change in head as we go from one to the other. What we could do is we could write Bernoulli between these 2 points and take it on 2 different routes. We could take the low road and the high road, as you might say. We go through pipe 1 in both cases, but in one case we'll branch off to the top side and we'll end up in this tank via this top pipe. And the other case we'll do the opposite and go down through the top pipe. So the first route is this one between pipes 1 and 2. And if we write Bernoulli between each of these cases, we have the conditions at this point here, the conditions at this point here, which are these 2 values, this one and this one. And then in addition to that, we have the head losses that occur in this pipe and this pipe, which are these 2 things here, this and this. So that's what we've been used to writing Bernoulli as before. If we take the alternate route from A to B, which goes through this bottom pipe, so it comes through here and goes along here and down through here and up to here, just a different route. Again, we have the Bernoulli expressions at A and B, which are these parts here and these parts here, which are identical, by the way, between these 2. And we have the head losses that occur due to flow in this pipe, which is the same as this one, right? These are both equivalent to each other because they're both occurring in the same pipe. And also this amount that's due to it coming in this pipe, whatever the velocity is, which you perhaps don't know yet. And so what we know in each of these cases is that this head loss that occurs in the 2 pipes that come from this bifurcated junction here into each of these has to be the same. And of course it makes sense that it's the same because they'd have the same pressures at this point, and now they're going to a different pressure in the tank, and so it makes sense that the head loss to get to that same pressure in the tank has to be the same in either one of them. So we could assume that for these bifurcated systems, then this head loss has to be the same in both these final pipes, pipes 1 and pipes 2. Sorry, pipes 2 and pipes 3, not pipe 2, right? Here and here. And so that's the third rule, if you like, for this when we have somewhat more complex systems. And so if we think of that, again, we have the requirement that continuity would say that if you look at continuity for this, and you write continuity, I suppose you could surmise that the flow rate in the first pipe has to be distributed in both of these pipes, so this has to be the case, right, as well. So that's the other condition. So as in the case for the series flow and the parallel flow, we had a condition on continuity and on head loss. Likewise here we also have a condition on continuity and head loss, these 2 conditions. And so you just have to think about these in terms of what the logical behaviors are. And this comes out, of course, because each of these components here on this side have to be the same. The head loss in this pipe has to be a single number, and so the only other variable which has to match up has to be that as well. Okay. All right. So let's do a couple of examples. One of which is a doable example. One of which is something that would never occur on a test. I think this one might have actually occurred on a test once, but so this is the more simple of the ones that we'll deal with. So what's the question? We have two tanks, upstream and downstream. We want to be able to run the tank without this extra pipe in it and figure out what's going through it. And we want to be able to dimension a pipe which we know the length of, but dimension it so that we increase the flow rate from the first case to 30% more than the flow rate. So the flow rate with one pipe, which we should be able to calculate, we want to be able to boost that flow rate by 30% by adding in a second pipe. So the question is, what are the dimensions of this pipe that we have to add to do that? So how do we go about doing that? What do we know, first of all? We know the elevations of the tanks. We know perhaps that they're big tanks. So the velocities at these upstream and downstream points are 0. The pressures are atmospheric. So the standard conditions that we would presume for these are exactly this in all cases. We don't know what the flow rate is in the first place. So let's call this Q1, Q original, and maybe Q, this would be Q final, right? So I guess that's wrong, isn't it? Already done that wrong. So we'd like the final flow rate to be 1.3 times the original flow rate, but we don't know what the original flow rate is. So how do we do that? Well, we write, it's not really a pipe system because we just have one pipe that actually has two sections in it. Bernoulli is for the upstream, for the downstream, the friction loss along this pipe, the friction loss along this pipe, no pressure upstream, downstream, no velocity upstream, downstream. We have the elevation difference between these two, which is just going to be whatever the elevation change is between these. We must know that somewhere. 25 feet, I guess, is this. So we know ZA minus ZB is 25 feet. And we need to know these other properties. We know the friction factor, just because it's given. We know the length of the pipe. We know the diameter of the pipe. And so the only things that we know, they're the same diameters. So by definition, velocity in pipe 1 and velocity in pipe 2 have to be the same, right, from continuity. So we know that V1 A1 equals V2 A2. So if we rearrange that, we end up with some expression, and we can solve for the only thing we don't know, which is the velocity in the pipe. If we know the velocity in the pipe, then we know also that the volumetric flow rate is just going to be the product of that velocity times the area. So we can get this. And so I guess this would be equal to our Q0, as I'm calling it here. So this is the magnitude we have. So we want the final flow rate to be 1.3 times that. And so we know that 1.3 times that would give us whatever that is. So I guess this is equal to Q final. And so now we want to figure out exactly what this diameter is. I guess that's the fundamental component that we want to figure out. So we can write Bernoulli's expression again. So if we do the first root, if we redo the calculation that we did before, but now instead of having a flow rate of Q original through this, now we're going to have a flow rate of Q final. So we've changed the flow rate from here. We still have the same 25-foot drop, but we're going to have a flow rate of 1.3 times that through this. And so we can write the same Bernoulli expression for that. It's the difference in heads between the upstream and the downstream, which is 25 feet. It's the head losses in pipes 1 and pipes 2. And we can just write it again in terms of these two friction factor terms. We know the friction factor. We know the length of the pipe and the diameters of both pipes. That hasn't changed. But what potentially has changed are the magnitudes of the velocities that we'll have in these pipes. We know this velocity here because V1 has to equal Q final over A1, right? So we know the flow rate that's occurring through here. we know the cross-sectional area of this pipe, and so we know the velocity of flow in V1 from this. And so if we write this out, we also know this magnitude here. So if we write Bernoulli between A and B that goes through pipes 1 and 2, which is what this expression is, so this is the root 1 and 2, then we actually know this velocity in the first pipe. We don't know the velocity in the second pipe, but we can solve for it. And if we solve for it, we get this value of V2. So now we know the velocity in this pipe, we know the velocity in this pipe, and so if we know the velocity coming out of here, so if we call that V2 final, I guess, and if we multiply that by A2, we get Q2 final, right? So in other words, we know this velocity, we know the cross-sectional area, and so we know the volumetric flow that's coming out of this. And we know the volumetric flow that comes out of the whole system, which is this. So I suppose Q final minus Q2 final has to equal Q1 final. And so the amount of flow that we need to get in this pipe now we know, because we have this, right? That's all. And if we know what that is, we can take this flow rate Q1 final, it's a volumetric flow rate. If we divide it through by the area final, we end up with a velocity in 3. No, sorry. I'm using the wrong number, aren't I? This is not 1 final, it's 3 final. Right? So in other words, well, big picture. We know the flow rate out of here. We know the total flow rate of the two of them. So the flow rate out of the bottom one is just the difference between those flow rates. If we know the total flow rate and know the flow rate out of the top pipe, the flow rate out of the bottom pipe we know. If we know this bottom flow rate, then we can define this as a velocity, and we can write Bernoulli between this point A and B, but going along this circuit, and we can solve for the diameter of this pipe that allows us to be able to get that flow rate. That's what we're trying to do. And so finally, we write Bernoulli between points A and B that is on the bottom circuit, between pipes 1 and 3. Before we did it on the top circuit, so this was this calculation with this not in place, and now this is this calculation with this in place. And so we know the velocity here, we know the velocity here, and if we write Bernoulli, we can solve for the thing that we don't know, which will be this. Right? We know what this velocity will be as a function of the diameter of the pipe. We know what the length of the pipe is. We know what the friction factor is. We certainly know what the velocity coming into this is, and also the dimensions of the pipe. And we also know the magnitudes of these head losses. Well, these head losses are these magnitudes, of course. And so the only thing we have to link up is this velocity in this pipe and the diameter, which are linked through this. And if we solve for that, we get a value for the diameter of the pipe. So it's just a matter of figuring out what you need to know. So to recap, we have a flow rate. When this is closed off, we can calculate the flow rate through here, and we know what that is. We multiply it by 30%. So now we know that the 30% flow rate has to come through here, and to be able to get the head loss along here, we can calculate what the appropriate flow rate is in this pipe. Once we know what the flow rate is in this pipe, and that the total flow rate has to be 1.3 times the original, we can calculate the flow rate in the bottom pipe. If we know the flow rate in the bottom pipe, we can write Bernoulli for this circuit, and we can solve for the diameter. So that's kind of. So it gets a little more complicated, and you have to be a bit more creative, but that's basically the way of doing it. So this, you'll be happy to know, is a question you will never see on a test, but don't switch off. And it starts getting more complicated, and perhaps we'll only do this in overview. And the idea is you have 3 tanks. And so you can imagine if you have 3 tanks, so if my hands are each a tank and my foot, which some of you can't see, is the other tank, then you can imagine if they're connected through the trunk of my body and you have these as open reservoirs at the top, then it will all flow out through my bottom foot at that reservoir. So if you take one of these tanks and you change the elevation, you could also imagine that it will flow from this tank and this tank into my foot. But at some stage, depending on the piping system, if the piping system, for instance, was really good between my arm and this arm, then what might happen if these were really low friction factor pipes, then the water that comes out of here would actually squirt out of this reservoir because it's a good connection. So you're never quite sure exactly whether it's going from these 2 upper reservoirs to the lower reservoir in my foot, or if you change the elevation of this one, whether it starts flowing from the highest reservoir out of the intermediate reservoir, and it depends really on the connections of the pipe. If this is a really narrow pipe and a thin capillary, then it would probably keep on going, both of them would drain into my foot, but if this was a really open pipe, then you can imagine it would just overspill if this was lower. And so in this particular case, you have an elevation of the surface at 850 feet, 838, and 805. So highest, intermediate, and lowest. And so one reasonable thing to expect would be that it could flow from these into this lower one. But of course, if this was a really great connection here for one, you can imagine that this would flow out of here and it would just flow over here. So there's subtle controls on the piping that you could imagine that if this was a big pipe, so it saw the pressure at this point, that it would just flow over. So to solve this, it gets complicated, but you basically have to make a decision on what the flow direction is. So if we assume that it's all flowing into this bottom tank, then Q2 plus Q1 has to equal Q3. So continuity is one assumption that you can make to close the circuit. So if you do that, then you have 2 basic circuits. So you could write, for instance, what do they do? You could write an expression from Bernoulli from this point all the way through to the downstream reservoir, since this is one of the flow directions. And you could write the energy equation, Bernoulli equation, from point A to C. And you end up with the head difference between the 2 reservoirs and the friction factors along each of these pipes. Right? That's what we had in the last question. Also, you could write, if we think that flow is going from this tank into the lower tank, you could also write the energy equation between B and C. So if you write the energy equation between B and C, it's the elevation difference between this tank, and it has to equal the friction factors along pipe number 2 and pipe number 3. Pipe 2, pipe 3. And so you basically have 3 expressions, so you have 3 equations, and you have 3 unknowns that you don't know. You don't know the velocity in this pipe, velocity 1, you don't know the velocity in this pipe, and you don't know the velocity in this pipe. So your unknowns are V1, V2, and V3. You have 3 equations, and you have to try and solve them. And I won't go through the solution of it, but that's basically the big picture. The big picture is that you have to use 3 equations to solve for 3 unknowns. It's a little bit involved because these 3 unknowns are actually squares of unknowns. And so it gets kind of messy. And so if you want to, you can go through this. So I will pledge to you that you'll never see that on an exam, but that's basically the idea. And I think the interesting thing is that you have to make some decision as to what is flowing where. It's clear if these 2 upper reservoirs are at the same elevation, that it has to go from the upper ones to the lower one. If one is at a lower elevation, it's not clear whether that is the case or whether it would overflow the intermediate one. Certainly it can't flow up from the lowest one into the intermediate one, but that's the other option. Okay. So that's kind of a quick view of pipe flows. So series and parallel. In series, the flow rates have to be the same, and the head drops have to be cumulative. In parallel, the head drops have to be the same, and the flow rates have to be, the head drops have to be the same, and the flow rates have to be additive, so you sum them up. And in the bifurcating pipe, it's slightly different in that you have this requirement where you have to sum the flow rates. This one has to equal the sum of these two, and the head drop in the second arrangement has to have to be equivalent to each other. So anyway, that's kind of closure on our pipe networks. We talked about measuring flows before. What is different now between the time we talked about them before is that we used Bernoulli's expression to be able to investigate some of these. There are three principal methods of measuring flows. One is kind of the Venturi idea of constricting flow and measuring the pressure difference, a bit like the pitot tube as well. One is to use force balance or momentum to be able to measure them. And the other one is to have a given volume and fill it. So fill a bucket of water over 10 minutes. You know the volume of water. You know how long it took to fill it. You know what the volume is. And so those are the three general methods. So let's look very quickly at them. The first one is to constrict flow. We've talked about it. So the idea is you have flow in a pipe. You put some kind of constriction in there, and you come up with a flow for the ideal behavior, which is a function of the upstream and downstream pressures, the density of the fluid, because you're killing the velocity of flow, and it's this inertial term that gives you the pressure rise that results from that, and as a function of the geometry of the orifice. So as you make this orifice smaller compared to the pipe, then you have a bigger pressure change because you're disturbing the flow more. You're stagnating more flow, if you like. So we showed an equation for that. The equation is just obtained by writing Bernoulli between these 2 points and solving and using continuity. But what it doesn't include, of course, because Bernoulli doesn't include viscous forces, it doesn't include the effects of viscosity on that behavior. And that can be important. So if you want to include the effects of viscosity, what you do is you take this ideal volumetric flow rate related to pressures which ignores the effects of viscosity, and you multiply it by some number which is calibrated for the influence of viscosity. And to do that, what do you do? Well, you just run fluids with different viscosities through it, or you run fluids at different Reynolds numbers and see how far it differs from the ideal case, and you've calibrated your system. And so these are just some examples of exactly that. This correction factor that you add to this as a function, not surprisingly, of Reynolds number. And it changes as a function of Reynolds number, and of course this is an indication of viscosity, because Reynolds number, you will remember, is the ratio of inertial forces over viscous forces. And so this, density, velocity, diameter, some limiting dimension, and viscosity. And as you change the Reynolds number, the magnitude of this coefficient changes. And so with very large Reynolds numbers, this correction coefficient shimmies down to the same value. It shimmies down to the same value because now viscous effects are no longer important, because it's mainly the inertial effects of large velocities that take over. We also talked about the fact that if you want to get a good reading of what the pressure, the velocity is, then you're better off with a Venturi flume or a very gradual nozzle. And if you look at the correction factors, when you start making this change in velocity very gradual and also not very big, then this correction factor that you use on this expression becomes inconsequential, right? It's about 6%, 4 to 6%. And so that's what you'd like, that you don't have to make much difference in it. And at very large Reynolds numbers where viscous effects are not important, there's also almost no correction whatsoever because it's only off by, this would be 2%, 1%, maybe 0.5% or 0.25%. And so it matters the magnitude of what the viscosity is. And Venturi flumes are even more gradual ways of changing velocity as you go downstream. So that's the first way of being able to measure flow rates. Force balance flow meters, I think it's the same way that your tire pressure gauge works, as long as it's not an electronic one. And that is that you have fluid coming along a pipe, and the pipe widens. So if the pipe is relatively narrow here, the velocity of flow is much larger. And so if you stagnate that against a static plug, then the fluid pressure will be larger than where the flow velocity is less higher up. If the flow velocity is too high, it'll exert a force on this little bead and it'll move it up. And it will move it up to a point where the pressure on this bead directly balances the weight of the bead. And so here the velocity will be slower, the pressure will be slower, and so by looking at where this little bead comes to rest within this tapered tube is some indication of what the pressure is or the velocity is that's coming out of here. Just because you can use Bernoulli and stagnation to be able to represent that. So a very simple way of being able to do that. You could use an impeller. So again, this is momentum. Fluid going against an impeller. The fluid's moving, the impeller is free to move. It rotates in this closed pipe. And if you count the number of rotations it does by having some armature outside, then you can measure the flow rate just by counting the number of rotations you have as fluid goes past it. So in both cases, you're destroying linear momentum. Here to physically push this up until you have the force acting down by gravity equaling the pressure force that's applied to it. And this is basically the force is acting on a turbine that acts against it. So you change the flow velocity and you change pressure is one. You destroy linear momentum is the second. And the third one is the so-called nutating flow meter. And it's really like filling a bucket of water over a given amount of time. And that is that you have flow into this region here. It fills up this little cavity. And once this cavity is filled, it provides a pressure that flips this little lever here to be able to expel the fluid out and then begin filling the other cavity. And so it measures one cavity, the other cavity, one cavity, the other cavity. And if you sum up the volumes in each of those and how quickly it changes, then you get some volume. So if you have very precious fluids, such as gasoline dispensing at the pump, or as natural gas being dispensed in these big tanks that you see outside people's houses, where you fill, I don't quite know how this works, you fill a volume, it trips this over and it moves around, and so you basically fill a volume and then discharge this volume. You get relatively accurate measurements of filling a bucket basically with water over a given amount of time and then emptying it, and then you can use that to very accurately figure out how much natural gas someone's sending you. So we've gone over a bit, but that's where we are.